Hello, welcome to 8.2, the area of a surface of revolution. So this is a little bit different than chapter 6. Chapter 6, we took a curve and we found the area under the curve. We spun it and created a volume, so it was a solid. This time we're only looking at the surface area. So if we have some curve, y equals f of x, and we spin it, we're only looking at the surface. If we were to lay this out flat, how much fabric or paper would we need to create the outside of this particular shape? So just to give us a slight idea on how this is derived, imagine I'm going to take a piece of it. I'm going to take a little piece of the curve right here. In last section, we talked about finding the length of that curve. And remember, inside the integral, we saw 1 plus f prime of x squared. And that helped us determine the length of that. And then I'm going to go between here and here. Right, so imagine if I took that shape and I opened it up, we're going to have an almost rectangular piece that we can somewhat approximate the surface area of this little piece that we cut out. Well, remember this height right here is determined by the length of the curve. So imagine we use our little template from our last section, 1 plus the derivative of f squared. And then the length of this is going to be, well, it's just going to be the circumference around. So it's going to be 2 pi times the radius, which is determined by a point in between the top and the bottom of this little strip that we have here. So we're just going to call it some point f of x between the top and the bottom. And now the area of this guy would just be the length times the width. And from that, we can see the derivation of the surface area, because we're going to take this right here and we're going to let it shrink down to 0, and in turn create the integral from a to b, 2 pi f of x, which is just the length of one of those strips times the height of one of the strips, which we got from section 8.1, f prime of x squared, and we're going to integrate that with respect to x. So here's the template that's used to find the area of a surface of revolution formed by a curve f of x. All right, so let's set up a couple of these. Find the surface area obtained. Do this. Find the surface area obtained by revolving the function square root of 9 minus x squared about the x-axis between -2 and 2. Well, we have y, or f of x, equals the square root of 9 minus x squared. So we have to find the derivative. 1/2 9 minus x squared to the -1/2. Don't forget, times the derivative of what's inside, which would be -2x. And then we're going to clean that up a little bit. That's just going to be x over, the 2's cancel, so it'll be -x all over the square root of 9 minus x squared. Now I need the derivative inside squared, so I'm going to take the derivative and I'm going to square it right now, so I'm not writing this integral over and over again. And it's going to be, well, if we square this, we get -x, square root of 9 minus x squared, all squared, and that nicely becomes x squared all over 9 minus x squared. All right, so now let's put it all together. The surface area is then going to become, we're going from -2 to 2 pi, the actual function, square root of 9 minus x squared, all times the square root of 1 plus x squared over 9 minus x squared dx. All right, now I chose this one because at first glance, this looks really terrible to integrate, but this is actually really kind of cool how we can work with this. Your first guess might be to jump into trig substitution or U-Substitution perhaps, but watch what a little algebra can do. Let's look at what's going on in here. I'm going to turn this sum of 2 terms into just 1 term by finding a common denominator. I'm going to rewrite 1 as 9 minus x squared over 9 minus x squared. And then I'm going to add that to x squared over 9 minus x squared. So I didn't change the radicand at all. I just put it in sort of like a different outfit, if you will, because I want to turn this into 1 term. So now I'm going to add the numerators and keep the denominators. So that radicand is actually just equal to 9 over 9 minus x squared. So this I'm going to just replace with this. Okay, so let's see where that brings us. This brings me to, I'm going to bring the 2 pi out front, negative 2 to 2. We got the square root of 9 minus x squared times the square root of 9 over 9 minus x squared. All right, do you see where this is going yet? Okay, so now this becomes 2 pi, negative 2, 2, square root of 9 minus x squared. Now I'm going to split this radical up. That's just the square root of 9 over the square root of 9 minus x squared. Pretty cool, huh? Those cancel. 2 pi, negative 2 to 2. The square root of 9 is 3 dx. So this horrible integral reduced down to integrating the constant 3. And when we do this, we get 2 pi times 3x. We evaluate that from negative 2 to 2. We get the surface area, 24 pi. Big fat 4, there we go, 24 pi. So sometimes these integrals with some clever algebra, maybe a clever substitution, do turn out to be pretty decent integrals. Not always. Let's look at this guy. Find the surface area obtained by revolving the function y equals 2 to the x between negative 1 and 3. So we have y equals 2 to the x. So the derivative is going to be 2 to the x times the natural log of 2. Remember the derivative of exponential functions. So the surface area is now going to be found by integrating 1 to 3, 2 pi, my original function 2x, right? And then it's going to be the square root of 1 plus 2x, the natural log of 2, quantity squared dx. All right, now kids, this would take me forever to do this out, but I am just going to kind of give you a little bit of guidance on how we would integrate this. To integrate this, the trick is to let u equal 2x natural log of 2. So then we would just have 1 plus u squared underneath the radicand. Then du would be, well, the derivative of 2 to the x natural log of 2 is itself times the natural log of 2 again. Because this is just a constant, so the derivative of 2 to the x is 2 to the x natural log of 2, and then we put the constant back in. So du is actually 2 to the x natural log of 2 squared dx. Remember, that's just a constant. So I'm going to replace this with u, and then the 2 and the 2 to the x dx. Well, I have 2 to the x dx here. I'm going to bring this constant over to the other side. So I'm going to get 1 over the natural log of 2 squared du equals 2 to the x dx. So then what you land up integrating is, we'll do 2 pi, and then 2 to the x dx is going to be the 1 over the natural log of 2 squared, and then we're going to integrate 1 plus u squared du. Now this itself is not all that pleasant. I'm going to bring that 2 pi out over the natural log of 2 squared, and then I'm going to do 1 plus u squared du. So to go about integrating this, not super fun. What I'm going to do is just give you a hint and then let you hash out the details, but don't sweat too much about it. It is a terrible integral. What I wanted to do is just to show you the setup. So the suggestion is to use table entry. Number 21, okay? And see where you can go with that. What can you do? And I'll just give you a hint. It's not pretty. So I'm not going to waste your time by doing how I did do it out. I'll show you I did this, and we got to this, and it got to be really hairy and ugly quick. And so I just decided to say, you know what, I'll let you plug it in if you're interested, but don't sweat too much about it, okay? All right, so that again was revolving a function f of x about the x-axis. What about if we revolve it around the y-axis? So the surface area obtained by revolving a curve x equals g of y about the y-axis, well, it's found the same way. We're just going to integrate from c to d. It's going to be 2 pi, and it's going to be the function g of y, and then the square root of 1 plus g of y prime, quantity squared. So with that being said, let's suppose we determine the surface area of the solid y equals the cube root of x from 1 to 8 about the y-axis. Now be really careful because this is all in terms of x. So what I need to do, the cube root function looks something like this, right? And I'm rotating it here. I'm going from 1 to 8 here. So what I need to know is what are these values here and here. So going from 1 to 8 on the x-axis is equivalent to going from 1 to 2 on the y-axis, and we have y equals the cube root of x. So in turn, that's telling me that y cubed is equal to x. So this is what we're going to use because we're rotating it about the y-axis. And the surface area is going to be found by, we're going to go from 1 to 2 pi y cubed square root of, oh, we got to take the derivative. So x equals y cubed. Dx is equal to 3y squared, right? And then we're going to square it. So it's going to be 1 plus 9y to the 4th under here, 2y. And how are you going to integrate this? Well, we're going to use U-substitution. Let u equal 1 plus 9y to the 4th because we can see we have y cubed out there. So it's going to be 36y cubed dy. Right? So 1 over 36 du equals y cubed dy. So in turn, you're going to integrate 2 pi oh, sorry, I lost my train of thought for a minute. Y cubed dy is replaced with 1 over 36. That's where that goes. And then it's going to be the square root of 1 plus u du. Nope, just u. Sorry. Let me do that again. I'll rewrite that. So we're going to be integrating. Our u integral is going to be 1 over 36. 2 pi, because the y cubed dy gets replaced with 1 over 36 du. And then we let u be 1 plus 9 to the 4th, so it's just the square root of u. There you go. All right, so then it's just really pi over 18, integral the square root of u du, pi over 18, 2/3 u to the 3/2. So our integral becomes, we're going to do, that would be pi over 27, because 2/3 times pi over 18 is pi over 27. And then u was 1 plus 9y to the 4th to the 3/2. And we'll evaluate that from 1 to 2. Okay, so it's going to be pi over 27. I get 145 to the 3/2. Not super nice. Minus 10 to the 3/2. Right, and that's the exact answer. We can't go any further with that, and I got that to be about 199.48. All right, so try some of those surface area problems, and I hope to see you soon on Zoom. Have a great day.